Okay then, so we're going to have a look now at normal approximation. So what this diagram is showing you is, imagine binomial, okay? So go back to binomial for a second. N and P, N and P, N and P. And can you notice that this one and this one both sort of seem to look a bit like a normal distribution? They've got that symmetry going on because of the 0.5 element. And then with this one, because the n is sufficiently large, it really sort of smooths out that probability. This is okay, but, you know, with limited n, it's a little bit harder to get quite the right shape. So what we're going to do is we're going to say that when we have a sufficiently large n and we have a probability close to 0.5, it seems to do quite a good job, this approximation that we've seen here. So we can, instead of expressing sort of binomial situations in binomial, we can switch them to normal. And you might wonder why we might want to do this, but there is a good reason. So if we're going to use a normal distribution, what we're going to do is we're going to say that mu, because we want to make this normal, right? Mu needs to be MP, and you might be wondering where that comes from, but imagine, for example, somebody takes 100 penalties and they have a 50% chance to score them. Well, you would quite naturally expect a value of 50, wouldn't you? So it sort of actually seems quite logical. In terms of our standard deviation, this result, along with the previous one, these can both be found in the formula booklet. Okay, so these are going to be results that we're going to need to use when we are doing an approximation. So approximate is really the key word here. So for example, instead of taking these binomial situations, what we could do is we could do NP. Okay, so NP would give us, say, 2 here, and we could do NP and then failure, or NPQ sometimes this is called. We could do the square root of this. So what we would find is we would get a variance for this one of 1.6. So that's sometimes called NPQ. I'm writing it as the variance rather than the standard deviation here. Okay, we would get 10 and we would get 5 there, you know, and so on. Okay. Now, you might just say, well, hang on a moment, you said I needed to use 0.5. And I did, but sometimes a question does sort of say that even if it's not a great fit, they can still ask you to do an approximation. So we are approximating a binomial distribution into a normal distribution. And we might want to do this because those binomial coefficients, NCR, this involved doing factorial calculations, and this is computationally very, very intensive. So a normal distribution is something that we might want to do. Now, another thing to be aware of, and we need to be aware of this whenever we are approximating to a normal, is that binomial takes discrete data, right? So typically whole number values. N is 1, N is 2, N is 3, something like that. But the continuous distribution of the normal means that we need to be slightly careful. So in the example underneath, I'm just going to show you what I mean. So imagine we were interested in a discrete distribution about finding the probability that something is exactly 6. Well, you may remember that in a normal distribution, it would have a probability of 0 because nothing is exactly a specific number. So what we have to do then is we have to adapt our normal distribution. And it seems sensible that what we would do is we would say that, sorry, that's not what I wanted to do. We would say that values from 5.5 to 6.5, and I could leave this hollow, but I could shade this in. Remember, in the normal distribution world, it means the same thing. We would say that if we wanted to find 6, what we would do is we would look between 5.5 x or y or whatever we're calling this to 6.5. Okay, so when do we do this? We are going to do this when we are approximating. Okay, so when we approximate, we need to do this sort of bound work that you can see here on the board. I've used X and Y there to stress the fact that they are different distributions, okay? So we've got a couple questions here on the board, and I want you to just imagine with each, say I wanted to find these and I was approximating, what would I actually look at? So here this says 5 and more than 5. So what's the first value that becomes 5? Because clearly I want to keep 5. Well, it's 4.5. So what I'm looking for is I'm looking for y. I've written it with the probability statement. I'm going to write it just without. So I'm going to say y is greater than or equal to 4.5. No lazy shortcuts here, please. Just think about the values you're interested in. And remember that the 0.5 above and the 0.5 below belong to a number that you're trying to find the value for. Here, we're interested in 5 and less. So what we can do is we can say that 5.5 still belongs to 5, and then we want smaller values. Okay, so we would do something like that. So that would be y is less than or equal to 5.5. Some other ones. So less than 9. Less than 9, well, less than 9 in a binomial context means 8 and lower. You can't have 8.5s and 8.2s and things in the binomial context. So it means 8 or less, and then we do the continuity correction, which is that everything for 8.5 and less should belong to it. Okay, so y is less than or equal to 8.5. Over here, greater than 9, means 8 and larger numbers. So we want the number 8 itself, so 7.5 also belongs to that. Okay, so 7.5. Yeah. All right, so these are all continuity corrections, and the idea is that we would want to do these 7.5 greater than. So I'm just checking my work a second. So 8 and more. So yeah, 7.5 should belong to it. Okay. So on the next slide, there are a couple of quick questions. So I would encourage you just to pause for a second and have a think about what these various values would be. So I've got y is less than or equal to 7.5. Less than 10 means I want 9. So the first one that belongs to 9 would be 9.5. Not greater than 9 means 10 and more, so 9.5 is the first one that belongs to it, and then it's greater. Let's do some of these in-between ones. 1, what's the first value that works for 1? So that would be 0.5. And 10, well, the 10.5 even belongs to the 10 as well, so something like that. A harder one here, so what's this saying? Greater than 3. Well, you might want to do an in-between step here, and you might want to say something like this. There we go. It's a little bit easier to answer it once you do something like that. So what belongs to 4? 3.5 belongs to a 4. What belongs to 5? 5.5 belongs to 5. Okay, and the one that we did originally was this one here. So the idea would be that you would do 2.5 y 3.5. Okay, you can often get a mark in these questions just for the continuity corrections. So it's a good idea to do. So this is a good way to do it. Okay, if we go on to our next question, so we're going to do a full question now. So giving this one a read. So for a particular type of flower bulbs, 55% will produce yellow flowers, and a random sample of 80 is planted. So what we would do is we would write out our values. So n would be 80. Probability would be 0.55. Remember, this will give us a good approximation because it's close to p. Mu is going to be equal to np, which is going to be 80 times 0.55. So I'll just have a quick look at my notes. So for this one here, this will be 40. So this is part B, sorry, that I'm doing first. So this will be 40. And then the variance is NPQ, or the square root of NP and 1 minus P. They mean the same thing here, okay? So this is 40 times, this is a little shortcut here, you can do the NP again, it's 40. So 40 times 0.45, and then you can do the square root of that. So if you do that, you get root 19.8. I'm going to keep it as 19.8 for the variance, yeah? So reason why I'm doing all of this is I'm saying that you can approximate to a normal distribution of 40 and 19.8. Sorry, not 40, 44. That should be 44. Okay, so this is the first sort of part that you normally do of a question, like part B. A, they want us to do the actual. So actual is the clue that you need to do this using the binomial, right? Because at the start, this is actually a binomial question. So what we need to do is we need to do, well, n is 80. So this is 80 choose 50. So it's 80 choose 50. 50 successes, so that means 0.55 to the power of 50 and 0.45 to the power of 30. Okay, this comes out as 0.0365. So I've answered this one kind of backwards. A, this is binomial. This has nothing to do with normal. This is binomial. Okay, whereas here, this is setting up for the normal approximation. And the idea then is that once we do the normal approximation, we can use that on 50 flowers. So I want to find the probability from 49.5 to 50.5. That's the probability of 50 in a normal approximation. Using this data here, you'll get 0.0362. So what you should notice is the normal approximation gives a really, really good approximation. If we do the percentage error, that's the final part, it is 0.0365, so it's the actual minus the estimated, and this should be divided by the actual times by 100. Okay, it gives 0.82% percentage error. So what it's showing you is because we have quite a large n value and a p-value of quite close to 0.5, you can get a great approximation from something like this. Okay, the test your understanding, you're going to have a quick go at. So pause the video for yourself and try it out. You will find that a half is the first one. So it works really well because then the binomial is symmetrical. And finally, you should get a NP value of 96 from your approximation. Your NPQ value, that's the variance. You should get for that one 49.92. And you need to do a continuity correction. So you need to do 89.5 to y to 105.5 using this normal approximation. If you do all of that, your final answer should be approximately 0.7055-ish. Okay, so there we go. That's how you do normal approximations. So continuity corrections are needed. This is in the formula booklet, which really, really helps you out. And we've had a go at 2 common exam questions there.